In this video, I will be presenting my fourth lab report on oscillation. The object of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. This will be done by constructing a model using VPython. First things first, let us observe the initial conditions of the concerned process. So in this system, the spring is 70 centimeters long, the mass of the object is 0.402 kgs. The origin is at the base of the spring. This is the motion concerned. The positions of the given mass with respect to the axis are tabulated and then saved in a CSV file so the actual motion can be compared to the predicted motion later on. Here, the CSV file is being read and is being written into a graph. And the ball's mass is specified as 0.402 kilograms. The ball's position was found through a tracker, and the ball's initial velocity is being taken as 0. The steps to predict the motion of the given mass includes choosing the system and the surroundings, identifying the forces that act on the system, and then also using the necessary formulas, and then drawing our conclusions based on the results of a VPython code. In this video, the system in consideration is the mass. We now identify the forces acting on the system. The contact force is the spring force and the distance force is the weight. Now the contact force or the spring force is equal to Ks, and the distance force and the gravitational force is equal to mg. Mg only acts vertically downward, so it's given by 0, negative mg, and 0. Now the spring force is equal to Ks. The time period of oscillation is given by this equation, and by squaring this equation, this is obtained, and by rearranging the terms, this equation is obtained. The value of m and t are known, and the difference between 5.22 and 0.66 shown here is the time period between 3 oscillations. Now by plugging these terms in these values, k is obtained. In order to find L naught, this procedure has to be followed. You may pause the video to observe it. While doing it, it's important to note that L is equal to the distance between the ball and the spring. Now know the magnitude of the spring force. Now the direction of the force is given by the unit vector of L. You can easily observe that if the length of the string is more than the relaxed length, the force exerted by the spring will be negative, else it will be positive. From this we know that Fs is a negative of Ks. So we now have the forces that are acting on the system. It should be noted that L hat is equal to L divided by the magnitude of L. Now we shall go about identifying more formulas and applying them for the system. We now know the force due to the weight and the force due to the spring. The net force is the sum of these forces. The work done on the system by Fg is given by the following formula. The delta R component of this formula can be found by following this process. Change position Rf minus Ri is given by velocity into time. This velocity can be found by applying the formula at the bottom right of the screen. Now that we have the work that has been done by Fg, now we have to compute the work being done by the spring force, which is equal to Us. This is equal to the integral of Fs ds, which would be equal to half Ks square Sf to Si, and change in the energy of the system is given by half mv final square minus half mv initial square. All of these formulas are plugged into the code. Ks that we had found is plugged in directly, and so is L naught. L is equal to the ball's position minus the spring's position, and L hat is equal to L divided by the magnitude of L, and S would be equal to the magnitude of L minus L naught. The formulas for K, Ug, and Us have been provided as explained. The F gravitational force and the F spring force have also been plugged in. In this code, the change of energy is calculated by calculating the initial energies first, and then calculating the final energies, and then subtracting them. Now we can form our conclusions based on the observations. When we run the VPython code, it would look something like this. In the code, the red line indicates the spring force, the green indicates the gravitational force, the blue indicates the energy change in the system, and the yellow indicates the sum of all energies. If you notice, the sum of all energies is always constant, and hence energy principle has been satisfied. The graph being written right now compares the predicted readings versus the actual readings. The predicted is given by the blue line and the actual is given by the red line. As you can see, the discrepancies aren't much. The extent discrepancies can be due to neglect of calculating drag force, neglect of accounting for the z-axis, camera distortion, and human error. Before we end this video, a certain other fact should be considered. Here are the graphs of the oscillation along the x-axis and along the y-axis. As you can see, the time period along the x-axis is 1.6467 and the time period along the y-axis is 1.52. This difference is due to the fact that the period of oscillation for different axes is different.